it was for, do you call it novices? So it was not a great extent. It literally ended at the Milky Way and clarity of the moon, but it was not super magnified to like see the stars and additional
Could you like see
universe.
Mars or Jupiter or Saturn?
Yes, I could see it when I was in the Eastern Cape. Mars was absolutely clear.
Okay.
When I moved to I could see Jupiter, I could see Saturn. I
Uranus?
could see the northern stars, if you call it that.
Wait. You mean like Aurora Borealis? Aurora Borealis?
I never knew them, but it's the northern star. Then onto the right, it forms the number 7
Okay. You mean constellations? I was thinking you're talking
constellation.
about what do you call those? The celestial, when there's
No,
green colors in the sky, but that's usually in the northern hemisphere, closer to the North
yeah.
Pole.
But also, if the satellites were moving, you could see them to a certain degree.
Yeah, this would be so cool to share with the other learners, eh?
It was wonderful. But
Yeah.
yeah,
All right.
it's unbelievable.
Okay. Let's start our class. Are we good to go? Hello. You still there? Are you on mute? Hello. Did I lose you? No. Hello. Hello. Oh, okay. That must be the.
UPS to electricity, so they didn't ask me.
Wait.
Sorry.
How does that work?
It's manual.
It's manual.
I bought a 200 watt battery, so to speak,
Okay.
to have the TV and the Wi-Fi, the fiber running. So now they went and switched off from the battery to electricity. So the fiber was just restarting.
Oh, okay. So what? You have to switch off, do the whole thing of switching from backup to normal on your own, like
No,
manually.
it's a handheld battery. You can take it anywhere. I use it for camping.
Oh, okay.
So you just unplug from the battery and plug back onto the wall for all the connections. So then you switch it
Oh,
off and then it restarts.
okay. So it's
So
pretty
she
much.
did it without, yeah, confirming with me what I'm in class.
Oh, okay. No, it's fine. Let's carry on. So it's just us, right?
Yeah, unless if you're expecting more people that we need to wait for.
No. I'm okay on my end. We'll end at around just after 8, and then is that okay?
It's okay.
Okay. Anything that you wanted to go through today?
No, I just want to make that comment of visuals during study. I'm shy.
You're shy, ne?
I'm
Okay.
shy.
I'm
Because
I'm
as you talk, I'm trying to follow along. Messing ngiyalahleka.
Oh, okay. I completely understand. Because now on my end, it's difficult to record and stream at the same time. So, but I'll try my best to explain as best as possible whilst we're following through the learning guide, because at least we've got that. But I also want to ensure that the video footage, when I write the notes, is captured.
Sure.
And as I upload, you get that in its quality, you know?
Yeah,
Right.
okay.
So, still on elastic collisions, I think worked example 12
Oh,
is
this
the
is the
same
project.
as worked example 11, which is where we finished off. So that can be self-study. I don't think we should do that in this class because I want us to ramp up our pace.
Yeah.
And that runs from page 47
48.
to
Mm.
page 49. And it's also similar to worked example 13.
Okay.
Yeah, they're similar. So you can definitely go over those in your own time. Um, I want us to discuss, but just to wrap up on elastic collisions. Elastic collisions, the momentum is always conserved and the kinetic energy is always conserved. Now, moving on to inelastic collisions, the momentum is always conserved, but the kinetic energy is not conserved, right? So as we go over our discussion, the inelastic collision is the kind of collision where the total momentum is conserved, but total kinetic energy is not conserved. But this kinetic energy is transformed from one form to another type of energy. Making the example of a car colliding against the wall, um, cars have what they call crumple zones, and we'll see that
Yeah.
in our discussion. So crumple zones,
Yeah.
like think about the part, yeah, the bonnet. It's
Yes,
designed
yes, yeah.
specifically so that it's soft, softer than the rest of the
Yes.
car.
To absorb.
The shock from the
Okay.
crash, right? Or you know this because you bought cars before. That's cool. So it's great that you know that. The front part is soft so that the energy of the collision as it smashes into another object is absorbed, and it I guess sort of lessens the blow, but that's a very layman way of putting it. um,
Is energy absorbed by the vehicle or the object of impact?
yeah, like I say, it's a very layman way of explaining it, but the best way to explain it is to say the modification of the shape of the car is where the missing kinetic energy goes. That's the best way to explain it. So it's not absorbed by anything. In fact, that energy of moving changes into the energy of squashing the soft part of the car.
Okay.
So that's where you see the change in the kinetic energy. So as it's moving, it's got a lot of kinetic energy, but as soon as it makes contact with the surface of the object it collides with, um, that kinetic energy starts to change. Now, eventually, all that kinetic or much of that kinetic energy changes the form of the shape of the car in the crumple zone. And as that change happens, that kinetic energy changes into the energy that deforms the shape of the car. That's where the kinetic energy goes. So the energy was used to bend the metal and deform the car. That's the discussion on page 51, those two paragraphs there. Another example is the example of, you said you had a telescope, and it's great that you did. You noticed the craters on the surface of the moon, right?
Yeah.
Right. So each of those craters is formed by asteroids hitting the surface, right?
Yeah.
So as the asteroid travels, it travels with a certain kinetic energy. And it's moving through space towards the moon. Now, as it's crashing into the moon, its momentum rather, the total momentum initially is the momentum of the moon, the initial momentum of the moon, and the initial momentum of the asteroid. The total kinetic, this is on page 51, right after the two paragraphs at the top there. The total kinetic energy is the kinetic energy of the moon and the kinetic energy of the asteroid. And this is before asteroid collides with moon. Right. So now it hits the moon. Once the so the collision is it's inelastical, right? It's inelastic rather. So this kinetic energy gets transformed into heat energy, right? So let's say now the moon is there and the asteroid has now hit the moon, and then it forms a crater. Now once it forms a crater, that kinetic energy is transformed into heat energy. And if the heat is large enough, it can cause the asteroid and the area of the moon's surface where the asteroid has hit the moon to melt into liquid rock. And now from the force of the impact of the asteroid, the molten rock flows outward to form a crater on the moon, and that's how craters are formed. So after this collision, the total momentum becomes the same as the total momentum before the collision. That's to illustrate conservation of momentum.
Is that the final momentum?
Yeah, the final momentum of the asteroid hitting the moon is the same as the initial momentum before the asteroid collides with the moon. But because the asteroid disappears, so to speak, quote unquote, doesn't disappear, the heat from the collision is quite large. Now, if that heat of the collision is quite large, then that asteroid melts into liquid rock. And now, after melting into liquid rock, you see like how lava is. That's something that's molten, right? So that molten rock flows outward and then forms the crater on the moon. So that change of kinetic energy of the asteroid into heat energy is where the kinetic energy goes. So that kinetic energy is not conserved as a result. Therefore, the kinetic energy before the collision is not the same as the kinetic energy after the collision. And for one simple reason. You want to guess what that is?
I'm visualizing why
Okay.
it's not the same.
Okay, what are you seeing when you're visualizing it?
Okay, the properties, number one, are different.
The properties of what?
asteroid and moon. But anyway,
Okay.
let's material. The moon has the what you call
The asteroid.
the comet asteroid has an additional aspect to it being the heat.
Okay. It's not necessarily an additional aspect, but remember, because of the heat, the rock as it is has now changed into molten
Changes shape.
liquid rock. So it's changed form altogether. Think about the crumple zone of the car. It's no longer nice and smooth, but it's like a piece of paper that you just tore off a page and then you squash with your hand and it crumples and crinkles up. So similarly, the rock changes from a big, very big boulder into liquid, like, like that you could pour out of a bottle. So the physical properties of the asteroid have changed, and I think that's where you're trying to explain. But here's another interesting thing. Let's talk about the velocity of the asteroid before the collision, because kinetic energy, velocity plays an important role in kinetic energy. Remember, kinetic energy is the energy of movement or motion, right? So before the asteroid hits the moon, it's moving, so it has a velocity.
Yeah.
After it hits the moon, does it still have a velocity?
As a unit, no, but as particles, yes.
Okay, maybe let's not go into that kind of detail. Let's just look at the asteroid as a unit, like you say. So, because it completely changes form and shape and physical properties, then in the change state, does it still have a velocity like it would if it was in its original form?
No, it doesn't. But the velocities should be the same of the moon and the comet on impact,
Not really.
not moving objects.
Not really. The velocities could be different. I mean, like you say, if it breaks down into small particles, those little particles could have velocity of their own, like from the asteroid. And the moon would probably still also have its own velocity since it's rotating around the Earth. Remember, we've done a couple of examples with that. But the point is, before the asteroid hits the moon, as a unit, it has its own velocity, just as the moon has its own velocity. Now, after the collision, there's no more movement of asteroid per se, but moon still moves the way it was moving anyway. So the kinetic energy of the system is now mostly just moon after the collision. But before, it's asteroid towards moon and moon. But after the collision, asteroid is kind of no longer asteroid and it's not there because its kinetic energy is changing into liquid. But the kinetic energy of the system is just moon, technically.
Mhm.
You follow?
I have to.
Okay, where did I lose you?
No, when you're making this example, I thought about the initial when we started with the momentum of the tennis ball.
Okay.
If it hits a court, it's different, the kinetic energy of the floor and of the ball. But if it were to hit the soil,
Oh, okay. Why do you make this example? I want.
it will be inelastic. If it were, it would be elastic. If it were to hit the net, it would be inelastic. But I feel like the impact moves an object, but on impact, the velocities should be the same. That's what I'm not understanding.
Okay, so I think. Okay, let me explain it like this, right? So with conservation of energy in in an elastic collision, right? The objects that are interacting would have different velocities before and different velocities after the collision or explosion or whatever. And this is because the energy is conserved, the kinetic energy is conserved. So maybe one object or two, or one of the objects, let's say the two objects are moving and then they collide. They each have different speeds towards the collision. After the collision, they have different speeds to what they had before the collision, right?
Yeah.
So none of the objects' shapes were changed. The objects didn't change form. They didn't get destroyed or altered or deformed in any way, shape, or form physically. They still maintain their physical properties. Tennis ball before the collision, tennis ball after the collision. Right. So now,
Depending on its velocity.
depending on its velocity, unless if you smack the, unless if like a tennis player smacks the tennis ball really hard against the wall, that the ball ruptures and it gets obliterated. That's a completely different scenario. There, the kinetic energy is not conserved. But if it hits the wall or any other object and it bounces back and it's still a tennis ball, the kinetic energy is conserved. But now, what I'm trying to make you aware of is that should the physical properties of the one object change, so the physical properties are, is it still the same shape as before?
Yes, yes.
If those properties change, then the kinetic energy is not conserved, therefore the collision is inelastic because you can see the change in shape of the object. So for example, in our moon and asteroid scenario, a crater has formed on the surface of the moon, meaning that its shape has changed. The asteroid has changed from being an asteroid to being molten rock. Its shape has changed.
Yes.
So the kinetic energy is not the same as before the collision for that system.
Yes.
Yeah, so that's what makes a collision inelastic. Should the kinetic energy change because the one object's physical properties have changed, then that collision is not elastic, it's inelastic. Yeah, so just keep that in mind, right? If two cars bump into each other with a high speed and none of the cars change shape, they're still the same as before the collision, which would be a miracle, then that collision is elastic.
It's elastic, yeah.
Yeah, so let's imagine rubber cars that can bounce into each other and people don't die. And the cars don't change shape, so insurance companies are out of business. So let's think about that scenario, which is probably not going to happen in our lifetime or many others to come on this earth. But we don't know that, but like I'm just speculating. The point is, should the cars be fully rubberized, that if they hit each other even at a high speed, they still maintain their shape, then the kinetic energy of those cars is conserved.
The kinetic energy of the system is not changed, therefore it's an elastic
Collision, yeah. Think about it this way. Ask yourself the question if the physical properties of the objects that are colliding change. For example, does one or two of the objects in the collision change shape? Like do they not look the same? Do they look different than they did before the collision? That's all you need to ask yourself.
Yes, if that's the case, the kinetic energy is not the same as before the collision. And then it's inelastic.
It's inelastic, yes.
The kinetic energy of the system
is not conserved.
Is not conserved, yeah.
Yeah. So just make a note of that. And I want us to do worked example number 14 on page 52.
Yeah, the
inelastic collision, right? Today is 22nd Feb. Right, so we're gonna do that. So we've got two cars. Car 1 has the following physical properties. Its mass is 500 kilograms and it's moving at 0 meters per second because it's at rest.
Yes.
It's stationary.
Yeah.
Car 2 has the following physical properties. Its mass is the same as that of car 1, so it's 500
But
kilograms.
it's moving at 2.2 meters per second to -1.
And yes, its velocity is, let's take to the left as positive. So its velocity is 2 meters per second. So to the left is positive. We'll just assume that for now.
And it says to the -1, if I'm reading it correctly.
Oh, no. That's how we express the units for velocity. Remember, meters per second would be distance over time, distance divided by time, which gives us the rate of change of distance or displacement. And that just means how fast are you moving. Remember when we started science class, I'm traveling from Polokwane to Nelspruit to come and give class, and my speed would be how much distance do I cover in how much time. Remember that definition?
Yes.
Yes. So the rate of change of distance between where I am and where I'm going is my speed. And if I add a direction to it, which is from Polokwane to Nelspruit, then I have a velocity.
Yes.
Yeah. So that m times s to the power -1 in exponents, it's the same as m divided by s, which is the s has a negative exponent, so it's m times s to the -1. Okay, so that's just a little bit of some math. However, we're told that the cars collide inelastically. So immediately when we see that they collide inelastically and stick together, we know that the cars deform, right? The cars change shape. And because the other one, sorry? The kinetic is not conserved 100%. And once we're told that they stick together, the question is now suggestive, which is that what is the resulting velocity of the resulting mass of metal? So once they collide into each other, it means they move together. And the final velocity is going to be the sum of the masses times the velocity of those two cars moving together. Right, so now on page 52, what we will see is that since we've chosen a frame of reference, left is positive, or to the left is positive, we can proceed with our calculation. Now, once we proceed with our calculation, we can say that the initial momentum...
I got it. Yeah, okay. I missed the what do you call it? The velocity. I didn't get it right. Okay, let's go.
Okay.
Yeah.
We'll Did you do the calculation just now?
Yeah. But then I'll scroll down and then I'm like, okay, cool, whatever.
Okay, that's fine. We'll do it together. Working together, we can do more.
Watch ANC. What for the ANC, you and I are done.
Well, this is not political class, so I'm not going to comment on that. But anyway, momentum of the first car is its mass, 500 kilograms, multiplied by its velocity. What's the velocity of the first car?
0.
0 meters per second. Cool.
Yeah.
And the momentum of the second car we calculate as it's what's the momentum again? It's mass times velocity, right?
Mm-hmm.
So what's the mass of the first car?
Five,
Of the second
500
car, rather.
kilogram.
Second car's mass
Same,
is
500.
500. All right, cool. And then what's its velocity?
The second car is 2 meters per second.
In which direction?
To the left.
To the left. And the left we said is positive, right?
Yeah.
Okay, cool. Now on the other side of the equation, we've got the sum of the masses. That's 500 plus 500, right?
Mm-hmm.
But now we're told that the cars stick together after the collision. So that means we have one velocity for the two cars.
Yes.
Alright, so we can add the masses first and then multiply with the velocity.
The final velocity.
The final velocity, yes. And then on one side of the equation, we've got 1,000 kilogram meters per second as the momentum, initial momentum. And on the other side of the equation, we also have 1,000 kilograms times the final velocity.
Yes, times final velocity.
And then we must divide by 1,000 kilograms on both sides of the equation. And what we end up with is that on the one side of the equation, 1,000 kilograms divided by 1,000 kilograms gives us 1. So we're only left with the velocity final times 1. And on the other side of the equation, the 1,000 kilograms divide each other out to give you 1, as well as the units kilogram divide each other to give you 1. And so we're just left with 1 meter per second that's positive, which tells us that the cars move to the left.
At the same velocity.
At the same velocity. So they both move to the left at 1 meter per second after the collision. Ne?
Yeah, no. The masses cancel each other out.
The 1,000 kilograms divided by the 1,000 kilograms give you 1.
Yeah.
And then you just multiply that with the final velocity, and that's why you have and then on the other side, the 1,000 kilogram meters per second divided by 1,000 kilograms, the units divide each other out to give you 1, and the thousands divide each other out to give you 1.
The masses.
Uh-huh.
One of them is the mass is 0, but the mass is 500, but the velocity or the movement is 0.
Uh-huh.
So why do you say it cancels each other out?
Okay, so on the side where we calculate the initial momentum, the initial momentum of the first car becomes 0 because the momentum as the product of the velocity times the mass becomes 0 meters per second times the mass of 500 kilograms. That's where we get a 0 kilogram meters per second, right?
Yeah.
So that has little to do with the second part, where the second momentum of the first momentum rather of the first vehicle, which is 1,000 kilogram meters per second. Those two are kind of not related directly. Because even though the other car is not moving, it has a 0 value momentum. The other car that's moving has a momentum that has a magnitude.
Can
Now,
I ask something quickly?
yeah, sure.
If it's moving at 2 meters per second, can we assume that that car is slow? Out
Right.
of interest, because the displacement is only a meter.
So here's the thing about the natural sciences, the physical sciences, right? Um, hot and cold are the same thing, but just different extremes of temperature. So you'll find when we do other parts of science that we talk about heat even if something has a temperature that you might intuitively perceive as cold.
Extreme or cool.
Yeah. So, for example, in the temperature scale, absolute zero is actually negative 273 degrees Celsius. That's absolute zero on the Kelvin scale, right? But relative to what you and I know as humans, hell, 273 degrees Celsius below zero is very cold.
You did.
Is very, very, very cold. You are dead. Liquid nitrogen has a melting point of about negative 200 degrees Celsius. And if you put a leaf of a plant in that, it literally becomes
Dries
brittle
up and crumbles.
and it can shatter, yeah. So, but we still refer to that as a kind of heat. You know what I mean? So what I'm trying to convey is that when you're dealing with the natural and physical sciences, if you're talking about speed just as a quantity, something that's not moving has a speed that has a value of zero.
It's conserved.
It's stationary.
Yeah.
Yeah, so an object that's not moving has a speed of zero. But as soon as it moves, then the speed increases.
Yes.
Yeah, it can move very fast. Let's say it moves as fast as the speed of light, then it has a very high speed.
Yeah.
Yeah. But if it's stationary, it has a speed of the value of zero. Yeah, so we use the concepts like speed, length, these dimensions, we use them to explain physical quantities that we make sense of the physical world with. Not necessarily to say something is too slow, too fast. Yeah, when we're speaking, it makes sense because that's how we intuitively interpret the world. But when now using the data that we use to calculate stuff like this in science, it makes a lot more sense to refer to it just purely as a concept that it is this construct, its speed, its length, its height, its temperature, its mass. Yeah, and if you say something has a negligible mass, it doesn't necessarily mean it's weightless. It just means you don't have to consider the mass. But what I'm articulating is we are not necessarily concerned with how heavy or light the thing is. It's one and the same thing, it's just mass. But a smaller mass differs from a larger mass.
Okay.
Yeah, I don't know if that makes sense, like if it paints a picture. But with the idea of temperature, for example, at absolute zero, that's where in science zero is regarded, at least in the physical science, in the third dimension. That's where things are considered to be really, 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 really cold. But it really just means the heat is absolutely not there. But as soon
Yeah.
as you get to 0 degrees, whilst you and I know that it's the freezing point of water and it's cold AF, it's still relatively warm. It's still like it's still a form of heat, so to speak. Let me
Because
put
of
it like that.
Kelvin's theory.
Because
or
of the
whatever.
Kelvin scale, yeah, it's still a heat,
Kelvin's scale.
so to speak. And now, when you get to temperatures where metals like gold and iron, steel rather melt, that's heat, but like a much higher degree of heat. So
Can I make a quick request?
yeah, sure.
Can I have a 30-second comfort break? Just 30 seconds.
Okay, knock yourself
All
out.
right. All right. What the hell? Damn. Ouch. Oh man, that was painful. Okay. Damn. Ow. I'm back.
All right, welcome back. Did you hit your pink little toe against something?
My arm got caught on my son's bathroom door. Damn.
Oh,
Okay.
okay.
So weird.
Alrighty. Yeah. So let's move along. Our time is almost running out. We want to discuss impulse, right? And the definition
Sure.
of impulse is that it is the net force. It is a product rather of the net force that's acting on an object times the change in time that force acts on the object.
Net force of object times change in time.
Yes, so so let's think about it this way, right? When a force acts on a body, it will result in an acceleration, and that acceleration changes or alters the motion of the body. So a large net force will cause a larger acceleration than a small net force.
Like when someone punches you on the face.
I guess, yeah, and you get whiplash. I guess, yeah, that's a way to put it. So the total change in motion can be the same if the large and small forces act for different time intervals. For example, um, the
Oh, wait, Ponto.
yeah.
I just wanna. This is what I imagine. I don't even know what it's called, but it's those metal silver balls banging on each other.
Oh yeah, what is it? Like a pendulum.
Is that impulse? But they're all the same size, so it can't be.
I think there's a part where we discuss something like that, and we're gonna have an interesting chat about that. But let's think about it in another way as well. Um, let's say, okay, to move a truck, you need a large force, right?
Yeah.
But the mass of the truck is so massive that the truck moves, but it moves a lot less faster than if that same force was applied onto a car, like your size car, right? So even if the same force acts for the same amount of time on the different mass objects, the smaller object will move a lot faster and a lot further than the larger object.
Yeah.
So think about impulse from that perspective. So
Yes.
from
Yes, yes.
yeah, so now we're exposed to the idea that from Newton's second law, which is that the acceleration is a product of the mass of the object times its acceleration. We can also interpret that in terms of momentum and time, where the net force is the change in momentum divided by the change in time and that means the change in momentum is the product of the net force times the change in time. So basically, a change in momentum, that's what gives you an impulse.
Final net of momentum. What's that triangle?
It just means a change in something. So it's usually a final
Change in
measurement
time.
of a quantity, subtract its minus the initial quantity or something like that. So like let's think about it in terms of gradients, right? When you're doing math and you're working out the gradient, the slope of a straight line, the gradient is delta y over delta x, meaning the change in y over change in x. And remember that example I made about if you're looking at a steep hike, right? To see that it's steep, then how high you go compared to how far you travel. So the change in height, the final height versus the initial height, divide by the final point where you end, which corresponds to your final height, and the height, the horizontal distance where you started. Um, that is indicated with that little triangle. It's a Greek symbol that means delta. That is delta. And it just means a change in. So we use that a lot in math and science. So a change in something, change in time, change in momentum, change in horizontal direction, a change in vertical direction, etc. So delta is used a lot to illustrate that there is a change in quantity, that specific quantity that you are observing.
Pulse is change in momentum. Yeah.
All right. So impulse equals the change in momentum of an object, and for a given change in momentum, then the product of the net force and the change in time is fixed. Thus, if the net force is reduced, then the change in time must be increased.
Yes, that makes sense.
Why do you say that? That's interesting.
Because the force applied to a larger object is more time for change in momentum.
Okay. Make me understand your thought.
That's wrong.
Make me understand your thought with the truck and car example.
Okay, so if I apply a push factor of 500 kilograms to a ton, it'll take me longer to move the object, but 500 kilograms to 1 kilogram will be faster for me to move the object.
Okay, I see what you're trying to get at, using the different masses of objects. That's it shows that you're grasping the concept. I like that. You can also think about it like this.
Of force.
Eh?
Okay, yeah, I must think about it as.
You can also think about it like, if you think about it with the truck and the car, right? If we're using the same force to move a truck as we're using it to move a car, then if I reduce the force, I would have to push the truck a little longer. To bring about the same change in momentum that I would have in the car.
Why is it wrong if I say if the force is the same, the momentum is different because there's more time applied to a greater mass than a lesser mass? Why is that wrong?
No, I didn't say you're incorrect. I said there's also another way to think about it.
Oh,
Yes. There's another way to think about it. But long story short, um, if you must
okay.
if you must apply a force onto an object and for some reason you have to reduce that force, then you have to change the amount of time that the force is applied to get the
Yes.
same change in momentum. That's the long and short of it.
Okay.
Yeah, that's the long and short of it. Um, in a few minutes, we should be prompted to extend the time. But anyway, so on page 54, there's a interesting graph there.
Yeah.
So on your horizontal axis, you have the time in seconds, and on your vertical
Yes.
axis, you have the force in Newton.
Newton. Yeah.
Yeah. So the that graph illustrates that when a force acts on a body, and that force is constant, then the application of the force over that time doesn't really change. So our force is pretty much constant and it's applied over a certain amount of time. But that's just
Yeah.
the relationship for how force acting on a body changes with time. Now, for the same force, should we want to plot out the impulse, then that looks a little different and it peaks like that and then it drops.
Yeah. I just drew over it.
Just drew over it. All right, but don't fuss much about it. I think what's important is understanding
Applying
how
the
we
force.
apply these in a context where we are calculating them, right? Like, I think we should pause here, and then in our next science class, we're gonna carry on from worked example
15.
15. So, what I would
Do you have
encourage,
do you
sorry,
have a reference of a video for this
for this.
impulse?
Um, we discussed it, so I'm still in the process of uploading those. Like, please bear with me. But once it's up, you'll definitely follow along through the class that we had. However, the important thing about this is that worked example 15 and 16 actually illustrate the concepts quite well. So just
Okay.
run over them, try and test your understanding of what we've done so far, and try apply yourself a little bit more. So like use it as a challenge to see how far you can go with it. I mean, if it's worked example and the answer is right in front of your face like that, it's tricky at first to try and make sense of it. But if you go with it step by step, then you will make sense of it.
Yeah, I know. Changing time is the mass over the next force multiplied by the final velocity minus initial velocity.
Okay, that part is actually, yeah, it's like change in momentum and you're just making one the subject of the formula. So it's basic math there.
Yeah.
Like if you think about it, initially, like the change in momentum is mv final minus mv initial.
Mm.
And then if you take out a common factor of the mass, then you have m into open bracket v final minus v initial.
Initial, yeah.
And then you divide both sides by the net force, and then you get the change in time. So
That's the impulse.
that would be the impulse, the change in momentum, definitely.
Okay.
Yeah. So I'd encourage you to do that.
Yeah, that sounds very interesting. Okay, cool.
Yeah, try that one out, and then yeah. So Saturday you still won't be able to come through, ne?
Saturday ngikhona. This Saturday angindawo ngizobe ngisendlini.
Awesome. Then we're gonna have class, all three of us. That is fantastic. I can't wait.
Yeah. Kusasa une-load shedding.
Yeah, I've got load shedding at 7. But I'll update you throughout the course of the day.
Okay, cool, no problem.
Yeah.
If you let me know by, please, it's not a force, it's just a request, by at least 3 o'clock, because that's when I knock off.
Okay.
And I know exactly how to plan the rest of my day for availability at 7.
Okay, that's fine.
Unless if you want me to stay at work from 3 to, I can only stay up until 4 o'clock because my son, after Kpela will pass 4.
Oh, okay.
Yeah, so I can stay at work from 3 to 4, it's not a problem.
I'll let you know during the day, so hopefully by noon I should have updated you.
Okay.
Wonderful. Let's catch up. I'll let you know about my schedule for load shedding tomorrow afternoon or noon, and then I'll also see you on Saturday if we can't meet tomorrow.
Cool, no problem. You'll see on Saturday if you can't meet tomorrow.
Yeah, well, I'll see you on both days.
Yes.
If I can make tomorrow, I'll see you tomorrow and Saturday. But if not, I'll just see you Saturday.
Okay, I'm gonna use the last 30 minutes to try and understand impulse.
Okay,
Okay.
awesome. We'll speak.